Okay, I guess we are live.
Hi everybody, can you hear us proper? There we go.
Brilliant.
So as you can see, this talk is about observability, Apache Flink, and Prometheus. I'm still seeing somebody putting their headsets on, so let's see, yeah. So before we start, we wanted to do just a quick round of questions, so like if you can just raise your hand. Does everyone here have some experience with Apache Flink or stream processing? Okay.
Good number. Is anybody is familiar with Prometheus? Well, quite more. Good stuff. So we hope, well, for the few people who are not really familiar with any of them, we are hoping you will learn something new. But for, I would say, the majority who are familiar with either, we are hoping we will give you some ideas to make them work together, make them work better together, Prometheus and Flink. So let's start with introduction very briefly. My name is Lorenzo Nicora. I am a streaming solution architect here at AWS. I'm based in London. I've been there for 10 years now, but I'm originally from Italy, as you probably get from my accent.
And hi everybody, my name is Francisco Murillo. I'm also a senior streaming solutions architect. I'm based in Madrid, Spain. Been on AWS for the past 5 years, but I'm originally from Venezuela.
And we also have our little mascot here, whose identity will be evident, hopefully, in a minute. So let's start. So we are going to talk about observability, of course. So why does observability matter? Observability matters because it gives you visibility on your system, and with this visibility, you have the ability to troubleshoot issues in real time, any issue that is happening on your system in real time. And the result is giving your customer better experience because your system will work better, and ultimately, this will give better revenue from your application and, of course, from your business. So observability itself is an operational concern, but the impact is definitely a business concern. And we usually think about observability in terms of observing IT infrastructure, application, compute resources in general, data, middleware maybe. But the thing is, what we need to observe is actually the business, okay? In the broadest sense. And we are not talking about KPI here. We are talking about observability in the very specific sense. And to observe the business, it means that you need to observe all the resources, all the technical resources that are part of your systems end to end, beyond compute, beyond your infrastructure. So you probably know, you're probably familiar with this. So the three pillars of observability: logs, traces, and metrics. Well, in this talk, we will be focusing on metrics in particular. This is also because this is a most relevant pillar when you're talking about observing something that is not IT resources, that is not compute. And sometimes this is the only observability data you have available when you're not talking about observing IoT resources. And what is a metric? So a metric is a series of samples of some measurement or something. It can be CPU utilization, can be temperature, so it can be anything, measured at a discrete times. And on the flip side, you can define a time series as a sequence of discrete data points, values, whatever they are, in chronological orders. So if you think metrics and time series are exactly the same thing, just looking at them from different point of views. And time series are often represented as line graphs. I'm sure you have seen many of them. They actually just represent the evolution of the value, whatever is the measurement, CPU utilization, temperature, whatever it is, over time. And a time series is stored are usually stored in a specialized database called time series databases. And these time series databases are actually everywhere, are in many, many more use cases that you would think, well beyond observability. Just to name some of them, in this picture we are just showing some of the possibilities. Name some of them. Well, trading and financial data, These are most of the time series, the trays, the prices, etc. Manufacturing and industrial application, monitoring the machines, for example, or monitoring IoT devices, for example, measurement, temperature, or whatever it is. Again, just to name some of them. And there are many, many popular time series databases around. Here we see just 3 of them. Amazon TimeStream, fully managed time series database by Amazon, InfluxDB, I'm sure you have heard of it, very, very popular, and of course, Prometheus.
But in this talk, we're just going to be focusing in talking about Prometheus. So what is Prometheus, for those that are not aware? Prometheus is a multidimensional time series database that we can use thanks to its specialized query language to do real-time visualizations, precise alerting, and it gives us a rich level of integration through its many connectors so that we can build those set of visualizations. But it also allows us to have multiple or different storage options if we need to scale our storage horizontally. Prometheus is designed for operational metrics. So when we're thinking about doing real-time dashboarding or the main use case for doing observability or monitoring, because it provides us that capability of doing real-time precise alerting. It offers its many features at a low cost at scale. It's designed to be able to scale and provide fast writes. And I would say that one of its key values or its key objectives is providing availability and data freshness over consistency. So as we mentioned before, this would be some of the use cases that we can see, and mainly we think of Prometheus just on IT infrastructure monitoring. But if we then take this as a time series database, well, we can extend this to its many different use cases. We can then use it for IoT device monitoring, manufacturing or industrial applications, fleet management, or telecommunications as an infrastructure. Why? Because for all of these different use cases, our main goals still remain, in which we may need to do real-time visualization, precise alerting, and also that we're going to be working and handling large volumes of data. So how can we write to Prometheus? Well, the most common way would be using its pull mechanism, that it works through scrapers. So our applications would expose their metrics through an endpoint, and Prometheus, depending on how we have set that configuration, it would pull the data, the metrics, through that endpoint at a set interval, and will load it and store it into the Prometheus database. It will do this, or some examples would be through a JMX exporter, or using an open telemetry as a unified standard. However, there is another way that we can actually enable Prometheus so that we can write data directly into the database. So instead of going through a pull mechanism, we actually push the metrics, we push the samples into Prometheus. And we do this through its remote write interface. This works really well when we want our sources to be able to write directly into Prometheus. We want to have more control of what data we want to send and what intervals. So if we think of IoT, we may end up having devices that cannot be sending the data constantly and not being able to actually expose its metrics or samples through an endpoint. But there is some small caveat or consideration, because we're moving the responsibility of getting the data into Prometheus to the source. So if we want to take a look at a sample architecture of the pull mechanism, well, we can have our application. Mainly, we've seen that this would be with containers or Kubernetes clusters that are exposing their metrics or infrastructure metrics through a specific endpoint. We configure Prometheus to scrape those endpoints and ports, and they will then store it in its backend. And later on, through its own proprietary, let's say, its own query language, we're then able to use tools such as Grafana for doing our real-time visualization. But how would that look if we wanted to actually use its remote write interface? Well, in this case, we would actually need a component, a custom component that allows us then to receive the data from IoT devices or from other, let's say, other different use cases, and be able to use the remote write interface and push the data directly into Prometheus. So in this case, after we already have our data stored in Prometheus, we will then leverage PromQL for doing our visualizations, querying, and alerting rules. It gives us the ability for doing filtering and aggregations in real time, and it provides its own custom functions that we can then use, such as doing sum, counts, deriv, or rate. What is true is that with PromQL, there's some considerations. It doesn't allow us to do any enrichment or joins. So we will not be able, let's say, to merge different time series that we're storing in our database. But also, it doesn't give custom flexibility of doing custom aggregations. We only are able to work with the defined set of functions that Prometheus provides. And what is true is that if we're storing or we're working with large volumes of data and we're generating many time series, we might face that with high granularity and high cardinality, we're not going to be able to get the best performance when querying Prometheus. So if we come to part of our title and how we can then handle observability events, and we think about the use cases that we mentioned before, this exact considerations, it's something that we can find when we talk about doing IoT monitoring for operational metrics. Because we're talking about a high cardinality. We may be working with millions of devices out there. High frequency, we might have devices sending data every second or every half a millisecond. And more importantly, we end up seeing that these devices not always sending all the data that we need in order then to actually be able to build our visualizations or build our business logic. So we might be missing contextual information such as the model ID, where the device is coming from. So if we come back to our remote write architecture in which we wanted to push the IoT devices metric to Prometheus, this custom component now for this use case, or many others, should actually be a custom preprocessor so that we're able then to, if needed, do those joins, do those custom aggregations before we write to Prometheus using the remote write interface.
And here is where Flink comes to the rescue. Okay, so what is Apache Flink? Who is not familiar with it? Well, this definition here is from the Flink website. It's short, but it actually contains all the relevant key characteristics of Flink. So let's go through it very quickly. So Apache Flink is a framework and a distributed processing engine for stateful computation over unbounded and bounded datasets. So first of all, Flink is a framework. It's a framework to write your own applications. Okay? You write applications with Flink. But it's also a distributed processing engine. So Flink also allows you to run your application you have written with the framework and run it in a distributed fashion across multiple machines. And this allows you to scale horizontally. And this gives Flink the ability to scale hugely. Okay? It's also specifically designed for stateful computation. And what is a stateful computation? Well, as the opposite, a stateless computation are all those computations where one output is only based on one input. So you get one message in, one record in, you do any transformation, and you get one record out. These are stateless. Conversely, stateful computation are all those computations where an output actually depends on many inputs, on the history, whatever has happened before. And this can be arbitrarily simple or complicated. A very simple stateful computation can be calculating a rolling average, for example. Very simple, just counting. This is stateful, but this can be, again, arbitrarily complex. And Flink is designed exactly for doing this kind of job in a resilient way. Because doing it is easy, doing it in a resilient way, so not losing the count and the state if the application crashes and restarts, that's easy. And then the bottom part over unbounded and bounded data streams. They may sound odd if you're not familiar with Flink, but the gist is Flink actually has a generalized API programming interface that treats unbounded data sets, streams, data that never finishes, okay? And bounded data sets, tables, files, finite data, Flink handles them the same way, with the same API. It actually considers the bounded data set as a subcase of the unbounded. But Flink is designed mainly for unbounded. It's designed for stream processing. And this is actually the use case we are considering today. So we are talking about Flink for unbounded dataset processing or stream processing. So one of the most important characteristics of Flink is the ability of reading and writing from many, many different systems. And this is not exhaustive at all, okay? This is just showing some of them. And the system Flink can read from can be stream storage, like Kafka, Kinesis, Pulsar, can be message queues, RabbitMQ, again, just to mention some of them, can be databases, and can be also files on S3, even in streaming mode. Same story for the destination you can write to. Databases, streaming, messaging, file system, and different type of databases, of course. You can see, for example, Cassandra, any JDBC database, relational database, DynamoDB. Again, these are just examples. And in Flink, there are components called connectors. They actually, let's think like the driver that allow you to connect to a specific of the system. So there will be, I don't know, a Kafka connector, there will be a DynamoDB connector, there will be a Cassandra connector, and so far and so on. So there is one connector for each specific technology. So at this point, we understand how we can use Apache Flink in the case of operational metric pre-processing for solving the problem and the challenges that Francisco mentioned, because with Flink, we can very easily do enrichment, so adding contextual information to the raw events that are coming from the devices. So for example, adding the model. We only have an ID, and we didn't need to add the model of the device, as an example. You can reduce cardinality. So you might have many, many devices sending a lot of sensors, but you actually don't really need all of them. So you can reduce the cardinality, reduce the number of time series, let's say horizontally, okay? You can also reduce granularity or frequency. So every device is sending a measurement of the temperature every half a second. You don't really need this granularity. You can reduce it, and you can reduce it doing some form of aggregation. That can be a very simple average or something more complicated. You can, of course, do filtering if you want. So, for example, filtering out spurious data. Imagine a GPS position. When the GPS tracker loses the position, it starts sending random position around. Well, you might decide just to filter out when it's clearly moving around, so you have a tracking position only when this is reasonably precise. Again, options we are talking about. And finally, you can calculate derived metrics. So from multiple raw metrics, you can calculate other derived metrics with potentially any logic. So how do you make Flink and Prometheus work together? Well, if you are familiar with Flink, you may say, well, there is a Flink Prometheus metric reporter. This is a component of Flink. It's with the standard distribution. So why can't we just use this for sending our metrics, our process metrics to Prometheus? The answer is actually we can't, because this is not the connector you're looking for. This is not a connector. And the exporter, the reporter, the many reporter, Prometheus reporter is one of them, there are other reporters in Flink, actually designed to export internal Flink metrics. So they are designed to observe Flink, to observe your application, not to handle data. And this is a very different use case. What we are talking about, the use case we are talking about is your data, observability data from external system, IoT devices, whatever, and you're handling them. Different story, observing Flink itself, how it's behaving. But last and most importantly, the reporters are definitely not designed to scale. because they are designed to monitor, your own application that may expose 100 metrics. It may be many of them, definitely not more than every a sample every few seconds, and that's it. This is not designed to scale. So we need another way of doing that. So you can implement something by yourself. The remote write interface of Prometheus we mentioned is open, is well documented, is a standard, is over HTTP, so you can clearly implement your own custom component for writing. And actually, we met some customers who were doing that. The issue is you need to build something completely custom, and you need to handle everything by yourself. You need to build the protobuf payload, because the endpoint is expecting a protobuf payload with a very specific structure, and it's very structured. You need to build everything from the very bottom, on top of a low-level HTTP client, because there is no driver. There is no remote write driver. It's just a specification. That's it. You have the model of the protobuf, and that's it. You have to implement everything by yourself. And ideally, using an asynchronous HTTP client to be more efficient. But again, this is an option. Most importantly, you need to batch writes, because if you send one sample at a time to the remote write interface, it will never scale. So you need to be smart enough, batch the write, making sure you're not messing up with the order, and send a remote write, a single request containing many, many samples. And last but not least, you need to handle the various errors reported by the HTTP endpoint and retry in the way as the specification prescribes. And the remote write specification is very, very strict on allowing you to retry some of the errors, not absolutely not others, and retry in some specific ways. So you can do it, but you can do it by yourself. The good news is you can now use a new component, is a new connector that is part of the Flink ecosystem, is a new addition to the Apache Flink connector ecosystem, is part of the Apache Flink project, okay? It's not a separate component, and is actually an AWS contribution, open source contribution to Apache Flink, and you see here two main contributors and authors of this, okay? It's not just us, there are other people involved, but on this stage, there are the two main contributors. And this was actually released in the stable version, the well-tested version, quite recently, mid-November. Now completely available and documented, etc. And it supports the latest Apache Flink stables version. So 119 and 120. It actually works with 2.0, Flink 2.0. We haven't really tested, but Flink 2.0 is still in preview. No connector has been really tested with the Flink 2.0. It's probably working very well, but we haven't tested. But this is the same story for all connectors. So, but we will test it when Flink 2.0 will become more stable. And so the idea is the Flink Prometheus connector actually unlocks using Apache Flink together with Prometheus for operational metric pre-processing. So it's opening a new set of use cases. And it's unlocking using Prometheus beyond observing just compute and IT infrastructure. And in particular, it becomes interesting for observing massively distributed resources. This can be IoT devices, this can be connected vehicles. We will see a demo in a minute about that, but can be anything else you can imagine that emit raw events and you can and system that you can base metrics on. So before going to the demo and the architecture of this demo, let's go very, very quickly through the key features of the connector. So first of all, the connector implements fully the remote write specification of Prometheus. Prometheus is not a product. Prometheus is a standard. And this is one of the specifications of the API of Prometheus, and the connector is fully implementing the 1.0 specification. 1.0 is the latest available that most of the Prometheus backend implements. It's designed to optimize writes, write throughput, okay? And does it by batching, but also by scaling horizontally. And it scales horizontally leveraging Flink, because Flink is designed to scale horizontally, so you will have multiple parallel writers. And while doing it, the connector is designed to retain ordering. because if you're familiar with Prometheus, you know that Prometheus is particularly picky with ordering, with the order of the sample you send to it. Is also, you can also configure error handling to some degree. You can decide what to do when the endpoint responds with an error. And finally, the connector is actually based on the Apache Flink async sync, that is a base connector you can use to build your sync connector if you want. And this was also an AWS open source contribution a couple of years ago, and can be used if you need to build your own custom sync. It's sync only, not the source, to a destination, and you can leverage an asynchronous client to whatever is the system. I would definitely recommend to have a look at the async sync to build your own connector on top of it. So let's see how our connector works in a simple pipeline, a simple Flink pipeline, and specifically when we are talking about observability data. So on the left-hand side, we have the observed device. Whatever they are sending the raw events. We're not talking about the ingestion, okay? This is out of scope, can be anything. But eventually, these raw events are sent to a stream storage. Think of Kafka. Kafka is a good candidate, but can be many others. And then we have the Flink application. And the Flink application, we have, at the minimum, a source connector that can read the data from the stream storage you are using, the Kafka source connector, for example. Then you have transformations. We see here one, but we see it can be more stages of transformation. So you transform the raw event, and eventually you use the sync connector, the connector we are talking about, to write directly to the Prometheus backend, calling the remote write interface. So the sync connector that is running within Flink will take care of the protocol for writing, the retrying, the batching, etc., to send the data eventually to the Prometheus backend. So I will hand over to Francisco.
So now let's see how this will look in a practical use case. So for our demo, we're going to be working with connected vehicles. We're going to be working with over close to 100,000 vehicles. And our main use case is we want to build a real-time dashboard, trying to understand how our vehicles, or connected vehicles, are behaving in the field. So for this demo use case, we're going to have 3 types of events. So we're going to be receiving the RPM for our vehicles. We're actually going to be working with hybrid vehicles. So they're going to have 2 engines. We're going to have an internal combustion engine, motor. And we're going to be receiving its RPM. And we're going to also have, in our hybrid vehicles, our electric motor RPM. We will also be receiving how many warning lights are actually on in the vehicle. And our use case is we want to know what is the number of vehicles that are in motion. So pretty much if the RPM of either of the motors, it's different than 0. And also how many warning lights we have in our vehicles. But in this case, if you then imagine, we're going to be working with 100,000 vehicles. So we actually are expecting, what we would like is, not to know specifically just if an individual vehicle is in motion, but if we're able then to know by region or by a specific model of the vehicle, how many are in motion, how many have warning lights, so we can then tell through our dashboard if there's any issues. So if we go through the end-to-end architecture that we're going to be working, unfortunately, we were not really able to get 100,000 vehicles, a real 100,000 vehicles, so we're going to be using a data generator. This actually itself, it's an Apache Flink application because we're going to be simulating all of these events, and we're going to be sending it to Amazon Managed Service for Apache Kafka for the streaming storage. And later on, we're going to be using the preprocessor component that we mentioned as a managed Flink application, which will then show in a little moment the actual logic of the application. But in a brief overview, we're going to be receiving the data, we're going to do our custom transformations, building that derived metrics of identifying if the vehicle is in motion and how many warning lights we have, and then writing it to the Prometheus backend. We're going to be using the Amazon Managed Service for Prometheus, and later for our dashboarding, we're going to use Grafana. So we are also going to be showing so that we can then compare It's a different version of the exact same architecture, but instead of doing the pre-processing and doing the enrichment of the contextual information to identify the models of the vehicles, and also reducing the granularity by doing aggregations within the Flink application, we're also going to have just a standard raw Flink application that just receives the data from the 100,000 vehicles and writes it directly into Prometheus. So we can then see what could be the added benefit of actually using Flink as that pre-processing for operational metrics.
Thank you. So let's zoom in within the preprocessor application. We will look into the preprocessor application. I promise we will show you something running for real, but we want to explain you what you will see. And we will share the code, by the way, at the end, so don't worry. This is the logical structure of the Flink application. So as you see, of course, the data are coming from Kafka in our case, and on the right-hand side, they end up in Prometheus. We understood it. Internally, we have a number of steps, or processing steps. So the way actually a Flink application works, when you write a Flink application, at least when you're using the data stream API, that is, let's say, the most native interface of Flink, what you define in your code is literally every and each of these operators and the links between these operators. And we will see some snippets of code. You define them end to end, so you define what is called the data flow, logically, and declaratively, and in the end, you say execute. So declare the data flow first, and then execute. This is the model of Flink programming. Again, data flow model is not unique to Flink. It's actually covered by other frameworks, but specifically Flink is probably one of the most popular implementation. So let's go step by step through all this and see, again, some snippet of code. We will not dive deeper in any function. It will be too long, but online you can find the full code, the full working code. So let's start from the beginning, from the Kafka source. And there is nothing special here, to be honest. So we are defining this is the beginning of the application. We remove all the boilerplate of getting the runtime parameter, etc. We define a source. The actual definition of the Kafka source connector, the instance, is hidden within this create Kafka source method. I'm not going to dive deeper into this because this is something very, very common in Flink. You can find many examples in the Flink documentation. It's not worth spending any time. What maybe is slightly more interesting is the fact that we are defining no watermarks. And how comes? Well, the reason is for this specific use case, we are not using event time semantic. Our aggregation, our processing is not based on the event time. The event that is written in the event itself is actually based on processing time. We will be doing some windowing based on processing time. And processing time is just system clock, okay? It's just simple. But it would work for in event time as well. It just, in this example, we kept it simple and we are defining no watermark. And watermark are the tool in Flink that is used for implementing event time semantics, okay? I'm not going to talk about watermarks more because it would probably take a session entire talking about them. In this case, we are not using because we don't need them. Last, but maybe more also important, I don't know if you noticed this at the end, this is not really related to our use case, but we are defining a UID on our operator, on our source. This is a general recommendation if you're familiar with Flink. Always set the UID on every operator, and this will save you many troubles when you try to evolve your application. Again, I'm sorry I don't have the time of diving deeper on this, but keep an eye on this UID and in your application, and if you're not doing that, please look at the documentation why that is important. But let's go to our actual application. So this is the next step. This is the enrichment. Okay, logically, it's just a map. One message in, enrich, one message out. So we have the raw events are called vehicle events in our application, and the output, we called it, well, with a lot of fantasy, enriched vehicle events. So logically, just a map, very simple. What is happening within this map? Well, in a real use case, you will probably have a lookup to some reference data set. So the raw event only contains the vehicle ID, like the VIN, for example, not the model. So we need to have somewhere a table saying, well, given this ID, this is the model. in Flink, there are many patterns for doing this. You don't need to naively just look up into an external database every time you receive an event. There are really many patterns. You can cache it. You can pre-stream the data set. You can keep them in Flink state. We actually have at least three blogs in the AWS blogs talking about different patterns for enrichment. I would recommend to have a look depending on your use case. In this case, we keep it simple. We are just, again, with the simple logic internally, we are just looking up a very simple table and add the vehicle model again. So the enriched vehicle events will also contain not just the metrics, not just the vehicle ID and the time, but also the model of the vehicle that emitted this event. And then here we branch. We have two branches in the logic, okay? Because we need to calculate two separate derived metrics. One of them on the bottom is the one for calculating the warning events. In this case, we are just calculating the unique number of warnings they're on, okay? We keep it simple, but it can be arbitrarily complicated. So what do we do here? Well, first of all, we filter out any event that is not an event related to warning. And then the three bottom lines are the aggregation of this. So the key by is a partitioning by vehicle model and region, because what we want to do is calculate the number of unique warnings by vehicle model and by region, not by single vehicle. We do a tumbling window in processing time of a fixed duration. This is a parameter. In this case, is set to 5 seconds. Probably something around that reasonable, but you can configure it if you want, depending on your use case. At the bottom, there is the actual calculation. That class here, warning process window function, we're not showing it, but it is just Java that is doing this aggregation very simple. There is nothing particularly interesting to that. And again, we are setting the UID here. Don't forget the UID in your application. On the top branch, we are doing something very similar. So again, filtering, in this case, we need to take into account two separate type of events. The internal combustion engine, RPM, and the electric motor RPM, because we are calculating a derived matrix out of two. In this case, the logic is super simple, but can be much more complicated, and you can consider many more metrics. But the rest, in this case, is very similar. So we do a key by vehicle model and region, because we want to calculate this derived metric by model and region. This will be the dimension of your derived metrics. And again, tumbling window and process to do the aggregation. And at the end of the application, we just need to, in this case, we decided to merge the two flows because the actual objects are the same. You can do it differently. You can have two different sinks for the two processing. It's okay. We just decided to go this way because it looks simpler in our use case. So we do a union. It's literally a merge of the two streams. We do a map that is a transformation between whatever is our object that is represented the aggregated events to the object that is required as an input of the Prometheus sink. This is very simple mapping between one object, our object, into the Flink sink object. And it's doing nothing special. It's mapping a POJO to another POJO. The key by is there for partitioning a parallel write, so we are sure that the data coming from the same time series are written by the same parallel writer. And this is very worthy class. Prometheus time series label matrix name key selector is not something you have to write. It's something provided out of the box by the connector. And is there, you just need to add this line, literally, copy and paste this line. And again, is done to ensure that the writer, the parallel writes, will retain ordering. So you don't have the same time series, sample from the same time series going to different writers, because this will generate accidentally out of order writes. And finally, we attach the sink. So we have this method, create Prometheus sink, creating the object of the sink. We will see that in a minute. And as I mentioned, after I define the entire flow, the data flow, the last instruction of the application, this is actually the main of the application, is just execute, run. But before finishing, and before seeing the actual things working, Let's just dive deeper in the last method, okay? The method that is creating the sink. It's actually nothing particularly special, if you want. It should be quite readable, even if you're not familiar. You will see in the documentation all the details, each method, what does. We're just getting the parameter from the runtime parameter. The only mandatory one is the URL of the endpoint, obviously. You need to reach it. Then in this case, because you're using Managed Prometheus, Amazon Managed Prometheus, we also need to provide the region, and we decided to tweak the maximum number of retries of the request, but this is optional. And then we have a fluent builder interface to build the object. As you see, we set up the URL, the endpoint URL. Because we are using Amazon Managed Prometheus, we need to add authentication, because Managed Prometheus requires authentication, and this is provided out of the box. So the Prometheus remote write interface doesn't specify any authentication. This is out of scope of the interface. So what we did with the connector is providing a general interface where you can implement your own authentication that will be usually adding some token to the request, or signature, or auth token, the usual suspects usually. But what we did in the initial version, there is an optional dependency that provides the Amazon Managed Prometheus write request signer out of the box. You just need to add it. And this will do the signature and getting all the credential automatically from the IAM role of the application if you're running Managed Flink. So you don't have to provide the credential. They will be inherited automatically by whatever is the IAM role of the application. And then we set the other optional parameter, and we just build it, okay? And oops, I switched before going to here. Please.
So now we're gonna see the actual demo in the AWS console, and we're gonna do it live, if we're willing. So if we then go to the managed service for Apache Flink console, we actually have 3 Flink applications. We have the vehicle Flink application, that is the one that we're using to generate the 100,000 vehicles. We have the preprocessor, which actually has all the logic that Lorenzo just explained. And we have the raw event writer, which is the one that is just receiving the data, the samples directly from Kafka, not doing any aggregation, and writing directly into Prometheus. If we go into the Flink dashboard of the data generator, we started it just before the session, and hopefully it's big enough, but if not, quite standard application. But then what's important is, if you notice, and hopefully you can see, we have already sent close to 500 million data points for our 100,000 vehicles, because each vehicle is actually sending 1 sample per second. If we then go to the raw event writer, we're actually then gonna see, we're just doing the map so that we do the transformation that Lorenzo mentioned, so that we take the metric and we made it in the specific format that the connector expects it. But from the close to 500 million events that we have received, that's exactly what we're writing into Prometheus. And if we go into the preprocessor application, first you're gonna see that the actual diagram is really close to what Lorenzo explained. Of course, within Flink, there's some operators that it's changed together, so that's more efficient. But I would like to just highlight here is, if we take a look on how many records our source has received, the 500 million, but thanks to doing the aggregation, thanks to doing the enrichment and the aggregation by region and model ID, we can then see that from the 500 million, we're actually just sending to the connector close to 300,000 metrics. So this is gonna help making Prometheus faster, because we're gonna be actually getting better performance, because when we query, we're actually not we're not gonna be scanning that many samples into Prometheus, and it's also going to be more cost efficient, because we're gonna be storing less. So let's go into Amazon Managed Grafana, which we have configured two data sources. We have one Prometheus, which is the one that it's receiving the pre-processed data. And we also have a raw Prometheus, which just has exactly the 500 million samples that we have already received and we're continuing to receive. So we wanted to show exactly what could happen if we actually try to use the raw data and just rely in Prometheus using PromQL to actually build our derived metrics and our aggregations. Here we can see that we are actually getting the raw metric, the electric RPM, the internal combustion RPM, and the number of warnings. And if I first would try to run this query, probably this will never finish. I'm not gonna pause it. So we're gonna see by doing some quick filtering by region. And I'm gonna go with Spain. If we then run this query, by filtering just to show the vehicles or the models that are actually in Spain, we can then first see, and this is only filtering 20 series. If we then want to take all of them, we can then see this is not usable at all. We're not really able to build any logic or understand what is happening with our vehicles. But here you saw first that that query took a little while. And here we can see just the raw data of its RPM. If we wanted then to be able to identify if the vehicle was in motion, we could build that aggregation by doing a count. Let me remove this one. Doing a count by region and doing a binary function that the RPM it's different than 0. If we run that query, it has to build it for us, get all the samples for Prometheus for the last hour. And again, we're talking about close to 500 million records that we have sent. It should finish. But again, we're working with all the raw data. I was not expecting it to take that long. There we go. So as we can see, not really meant for real-time dashboarding of our vehicles, but it's possible that we can build out those derived metrics or aggregations just by getting the metrics into Prometheus. But if we then go back to our pre-processed Prometheus, or more optimized Prometheus, we can then first see that we only have two metrics that are already our derived metric because we have that logic built into the Flink application. So if I go into the vehicles in motion, then we only get, well, now I can see the model and the region. I'm not gonna see the 100,000 lines that we saw before. So if I wanted to do exactly the same, filter out by region, and we go with the same country. First, you see how quickly that went. But also, we're actually seeing what we wanted. We're seeing how many vehicles were in motion per specific model, not its vehicle ID. And we don't need to do that custom aggregation of the count because we have already done that with the Flink application. So if we wanted then to take this into how this could look, if we wanted to monitor, let's say, our fleet of vehicles, we can then see in any given time how many vehicles are in motion and of course this use case is 4 vehicles, but it doesn't need to be. It will be any kind of data in which you can build and create your own derived metrics. Once that data it's available for Flink, we can see the number of warnings that are given in any given time. But also, as we're doing the aggregation by model and region, we can then see how many vehicles in motion are in the US. We can then see how many vehicles in motion are in a specific model. Of course, you can then see that apparently there's one that is quite popular, Nebulara, and then it makes sense that the one vehicle that is most in motion it's the one that has the most number of warnings. And the country that has the most number of warnings, again, would be the US. But this would be just an example, pretty much, on how Flink unlocks that ability of pushing the data at scale. This test is working with 100,000 vehicles. We have tested it with over 1 million. And we can then leverage Prometheus as a time series database for our use case.
Switch. Yep. Okay, and we are at the conclusion now, I think,
Yes.
well in time. Okay, so we have seen how Prometheus is a time series database that is optimized for real-time dashboarding and real-time alerting. It's often used to observe compute Kubernetes. It's very popular in the Kubernetes ecosystem, IT infrastructure in general, but you can open it to many other use cases. And these other use cases may pose some challenges, but using Apache Flink, you can pre-process raw metrics. And Apache Flink is the perfect fit for this work of real-time pre-processing raw metrics. And the Flink Prometheus connector we introduced actually unlocks the ability of using Flink and Prometheus together for these kind of use cases. And every time you need to observe data at scale. So the bottom line is every time you have to do real-time dashboarding or real-time alerting, and you need to do it at scale, especially observing widely, broadly distributed resources, like again, IoT devices, vehicle, or it can be anything. Using together Prometheus and Apache Flink with the connector, you can do it. And Prometheus is going to be very cost-effective for this kind of use case. So here are some resources. On the left-hand side is the link to the documentation of the Flink Prometheus connector. This is part of the Apache Flink documentation. You can find it. If you go to the Apache Flink documentation, the latest versions, you can see it. In the middle is the code of the demo we have shown. So this contains the Flink application, the three Flink application, the data generator, the preprocessor, and the raw writer that we show. And the idea is the Prometheus connector allow you to write data at scale to Prometheus. You can do it. So it's not a limited scale. Of course, it's going to be less efficient doing that. And on the right-hand side, you have the link to the two services, Amazon services we have used, in particular Amazon Managed Service for Apache Flink to run Flink application, and Amazon Managed Service for Prometheus as a Prometheus backend.
So before you go, I would like just for you to remember if you can then fill out the session survey in the mobile app. This is the way that we can then identify if this kind of session, this level of detail was a session that you really enjoyed. And by doing so, by scoring a 5, it allows us then for us to build a similar kind of content that you like to expect in reInvent. Thank you all for coming in too early in the first day at reInvent. So I hope that you have learned how we can then leverage Apache Flink and Prometheus for different use cases. If you were not familiar with those two technologies, I hope that this was interesting for you. And if so, thank you all for coming in again. Thank you.
Thank you.